Okay, so well, today's speaker is Carlos Nunez. He's going to start.
Tomorrow.
Yeah, sure. So this week's speaker, I guess, is Carlos Nunez, who should need no introduction. So he's visiting us from University of Swansea, and he's an expert in ADS-CFT and fantastic lecturer. So please pay attention, take good notes, and hopefully, you'll enjoy the event. So you know that there's a website for the course where the different venues are listed because we couldn't manage to book the same room for the whole lecture series. So anyway, today is here, tomorrow is in Lecture Theatre A, and then after that we're moving around the building. Don't follow me with the camera. Okay.
I'm trying to be professional here.
All right. So anyway,
so let me first say the truth. That is, thanks very much for the invitation. I'm really very happy to be here. So this is a course on some aspects of ADS-CFT. Jose was telling me that some of you are students, right? And some of you are not working on this topic. So feel free to ask any question you want. I think, and I really hope that the first lecture will be understood by everyone. And then in the second, okay, so some more advanced topics will start to be introduced. And then in the end, it will be about more precise things. But in the first lecture, I would like to discuss some general ideas of ADS-CFT. And I know some people have to leave, and it's okay, leave whenever you need to do so. But really, if you have any doubt, especially the young people in the audience, do not stop yourself from asking questions. So let me start this in this way. So let me start with a generic problem in physics. And the idea of duality as a solution. So let me consider just a particular problem in physics. Consider field theory. Consider field theory, whose degrees of freedom are a gauge field, this A. Okay, so a gauge field in SU3 has to be concrete, and fermions. And fermions, so it's a gauge field, and fermions, the gauge field is in the adjoint of the gauge group. The fermions will be in the fundamental. The Lagrangian I would like to consider is this one. And many of you will start recognizing this. So there are different fermions with a different mass term in principle for each one of them. Right? So this field theory, the field theory I want to have in mind here is quantum chromodynamics. Okay? So these are the quarks, those are the gluons, right? And this is the theory of nuclear physics. As you know, all the phenomena in nuclear physics, everything that happens inside the nucleus is ruled by this theory. Okay. So something that I guess even the youngest part of the audience know, all the rest know this quite well. If you compute, and this was done by Gross, Gulacek, and Politzer in 1973, if you compute the gauge coupling of this theory, the gauge coupling that, by the way, is here in the definition of F nu. Okay, and it's here also in the covariant derivative. So the idea is that if you compute this gauge coupling in terms of the energy, is not a constant, right? As people think about gauge couplings before quantum mechanics, but changes with energy. Right? And what's very interesting about this field here, and what makes this field theory and theories in this class very, very peculiar is that this gauge coupling does something like this. Okay. So asymptotically for very large energies it goes really very small. But then there is some scale. Let me call it lambda QCD, is the notation that people use, where this gauge coupling is basically 1. There are some things that I'm not saying super precisely, but this is the main idea. So this, by the way, is as I guess some of you know very well. This is a work that merited a Nobel Prize in 2004. So this is a very important piece of physics. The point that I want to emphasize with this is the following. If someone asks you to compute some observable from this field theory, right? So if the problem is the following, compute observables. Okay? By observables, I will mean compute correlation functions. Of gauge invariant probabilities, for example. So just to take an example, this correlation function. So computing these kind of things, computing these observables, is something that it's in principle, or at least algorithmically in principle, easy to do if you are at energies around here, right? So very far away from this scale. Why is that? Why is that? So I want to say that here the problem is easy, and I will explain in a second the quotation marks. It's easy because in principle you have a parameter where to expand, right? And make kind of a perturbative expansion of this. So how do you go about this? Well, you write this in terms of the fundamental fields, in this case the gauge fields. You start doing weak contractions, right? I guess that you're familiar with this from a quantum field theory course. You start doing weak contractions, and basically what you are doing is computing Feynman diagrams. Okay, so you do so, and computing 1, 2 Feynman diagrams will give you a very accurate result. So, and what I mean by the quotation marks in the easy is that sometimes with few Feynman diagrams you're okay, but many times you have to compute lots of Feynman diagrams, and people have developed techniques to compute those lots of Feynman diagrams, right? So the problem is easy, but not uninteresting. Right? So it's still an interesting problem. When you're in this region, the problem is by itself difficult. And there are no quotation marks here. Because it is difficult, right? And it is difficult because there is not a natural expansion parameter. Okay? So you have not a parameter, clearly it's not G and means, right? Because it's bigger than 1. So if you try to do some kind of loop expansion, the term that you're leaving out is bigger than probably the term that you already computed. So here the problem is truly difficult, and for this particular theory, the best solution to compute observables in this theory, in this range of energies, the best solution for QCD, I would say the only solution, is what people call lattice field theory. Okay. Then, of course, there are some field theoretical elaborations. Quantum field theory developments. People have developed techniques to compute in this region. There is always a certain degree of discussion about how accurate, how good these techniques, these schemes of approximation are. But in this particular example, at least, this is what gives the correct results. And of course, there is lots of experience about this, because this is something that comes since 1973. People are doing this kind of things since Wilson introduced lattice field theory, basically. So let me take this particular problem as an inspiration, as an inspirational problem, but let me try to generalize it a bit, in the sense that a more generic problem is how to calculate observables, if you want, in a strongly coupled quantum field. Okay, so this is the more generic problem, and this is the problem that I will try in one way or another address during the rest of this lecture. Right? So this is basically the problem. So I'll try to present one possible line of ideas for solutions, and these lines of ideas go under the name of duality. Okay. So sometimes it's not that easy in generic examples to work with lattice field theory or similar constructions, and these dualities give you a different perspective on the problem. Okay? So before I try to describe quickly what will I mean by duality, any questions or comments to hear? Don't be shy, it's okay? You remember that I used to say, don't be shy, yeah? Okay. All right. So let me try to discuss a bit about this thing. So what will I mean by a duality? So let me try to exemplify it. How should I do it? And it goes? Okay. So it responds to my voice. Okay. So let me try to exemplify this. I will not give a definition of duality. I'll just try to present you with two examples. Right? We can hook up other examples, but they all have the same flavor in the sense of they all have the same features, and are those features the ones that I want to pick upon. So the first example is an example that people in the audience, some of the people in the audience may know much more than me about this, and I just want to take the main characteristics of this example. Is an example that was developed in 1975, so it's old stuff. It's an example that works only when the dimension of a space is one space and one time. Right? So it works only in 2 dimensions. And it goes in the following way. Consider 2 quantum field theories. One is in terms of a real scale. One is in terms of a Dirac family. One of them has a Lagrangian that is given in this way. So I keep usual kinetic term for the scalar, usual kinetic term for the Fermat. There is an interaction here and now here. Let me copy the number. So if you are very probably familiar with the fact that this is the U1 current, right? So this is like the nether current of this theory. So this interaction is a current-current interaction. Okay? So it's the current talking to itself with a strength G. this theory has a very strange interaction, or at least we are not used to these things in these days very much. Right, so the potential is a cosine-like potential. Okay, and by the way, this theory when you study the quantum theory of this, by the way, I'm taking all this from two beautiful papers, one by Coleman and one by Mandelstam, that are in Physical Review 1975. So there are two very easy to find papers. They have lots of citations. You put them in Spires, Coleman, 1970s Physical Review, and immediately this paper appears. So what these two people propose in these papers is actually what at the time must have been a very striking idea. That is that these two apparently very different field theories are actually the same, are describing the same physical system. In other words, they are proposing that there is a duality between this theory and this theory. Or in other words, they are proposing that these two theories are actually the same. Right? So you look at this and you think, okay, this cannot be. But when you go over their analysis, they will show for you things like the following. You can define a current here that you can associate with the current here. You can define a soliton here. So if you want a solution to the classical equations of motion of that theory, that can be associated, and all this, the derivation of all this is, I'm not making this up, right? It's all in these papers. That can be associated with what in this theory is a fermion. But the most interesting point of this is this one that I want to copy precisely, that is the following. In this, when you do this association, by the way, this mapping goes under the name of bosonization. And if you study string theory on the worksheet, you may have crossed this mapping one way or another, but never mind, it's something that could be studied completely in the context of field theory. And it's basically a mapping between, it's a way of writing the fermion in terms of this scale. Right? We will not need that explicit expression. I just want to pick on the following ideas. And this is an important point.
Carlos, the equivalence that you write as a wiggly line means that the correlation functions of G nu are the same.
Indeed. So what they are showing, okay, Coleman suggests this thing. Mandelstam shows you the precise mapping between degrees of freedom here and degrees of freedom there, and then many people prove, and it's very nice to see this in the path integral. I can tell you a paper that does it in the path integral that is truly nice, that correlation functions of these currents computed in this theory are the same as correlation functions of this current computed in this theory, and similar with other observations. So in other words, the two theories are the same. This is the same theory, it's just showing you two different phases. The most interesting point of this equivalence, or if you want the most striking at the time, was the fact that whatever was the coupling here in this theory is related to the inverse coupling in this theory. Okay? So I would like to make a small plot here. You see, when your coupling beta, when your coupling beta is very small, your best bet to get some physics out of these systems is to study correlation functions of observables in terms of these degrees of freedom. So these are the good degrees of freedom to describe your system when your coupling beta is small. Okay? So in here, the scalar, or by the way, let me call it as people call it, the Sine-Gordon model, is your best description of these systems. Okay? And by best description, I mean it's the description that is naturally weakly coupled. On the other hand, if you are here, if you are there, what you will notice is that your best description is in terms of free fermions. Right? Because the coupling of the fermions goes to zero according to that. So the point that I would like to emphasize about this particular example of duality are actually 2 points. The first one is that the first point is that the degrees of freedom on the 2 sides of this duality can be completely different. Right? So in this case, it's not that dramatic. One is scalar, the other is scalar. Okay? But in principle, the degrees of freedom are very different. The second point, by the way, if you read Goldman's paper, you will see that the guy makes a very interesting point, that is making the point that scalar and a fermion in 2 dimensions are actually not that different. What distinguishes scalar from a fermion are the transformations and the rotations. In 2 dimensions, there are no rotations. That's why this thing works. Right? You can see it either that way, or another way of showing all this, and this is just a technical comment, is the fact that the algebra of the algebra of the gamma matrices in 2 dimensions, and only in 2 dimensions, is given by this. And from here you can really, using this, you can really make lots of tricks that allow you to show this thing. But okay, that's just the technical point. The second point I wanted to make is that the global symmetries, and I want to emphasize on global, and here is not that apparent, but it will be in the next. The global symmetries of both theories match in the following sense. You have a conserved current here, you have a conserved current here. Okay? And let me see if I want to make another point. Oh, yes. And the last point is that typically, and I don't want to generalize this to all the cases because it's not a universal thing, but typically, let me emphasize on the word typically. When one theory is weakly coupled, the other is strongly coupled. Let me call it, when theory A is weakly coupled, theory B is strongly coupled. Okay. So this you can see, for example, here. At this particular point, when beta squared is 4 pi, it would be really misleading to try to do a perturbative expansion in terms of these degrees of freedom. Right? It would be really a mistake because you would be leaving out loops that are bigger than the ones you already compute. So I'm going now to give you a completely different example of duality, perhaps a more interesting one. This example has the advantages that it's very well understood, and as far as I can tell, this is almost a theorem in mathematical physics. This can be proven, right? So this is really very solid. The next example I will give you is a conjecture duality, very much in this, in in this same kind of ideas, but I would like to emphasize in that second example that these 3 points stay the same. Is this okay? Is this okay up to here? Any questions about this? Don't be shy. So,
Okay, I won't be shy. So,
I don't know. That's the answer.
no, but so is this really truly an equivalence of theories, or do you have to restrict yourself to certain kinds of correlators that you want to do?
No, this is solid. There is a. So what Luigi was asking was, if you compute correlators of currents, do they match? Yes. If you compute correlators of any other thing, they will match.
Okay.
And this is because of the bosonization.
So this is the Boson-Fermi correspondence.
Right.
Truly
But the thing is that you will have to translate. So it may happen that a correlator that looks very simple in terms of these degrees of freedom looks very non-local and ugly in terms of the other degrees of freedom. Okay? But what's very interesting about this particular example is that thanks to the paper of Mandelstam, you know the translation. That is very non-trivial, and that typically does not happen in any other duality. Right? So that's very peculiar of this example.
I think in this case you can actually show that the two partition functions
Yeah.
are exactly,
That's
exactly
so
the same.
there is a very nice paper. There is a very nice paper by a fellow called it's a physical review D of 1995, where within the path integral he shows that, and it's very clean to see it with the path integral, right? It's very understandable. So if you are a student and you want to understand that, read this paper because you understand it. It's really a very clean paper. So let me give you a second example.
I have one small thing to ask here. I mean, here your alpha, I mean, is not playing any role at all.
This alpha is playing no role. Actually, you know, it will have to do when you expand this. Suppose that you are for small values of phi.
Yeah.
You expand this 1 plus phi squared. It's something like a mass in this case.
Okay, so it's not.
It is
not
actually,
really
you know, I
related to
shouldn't
the
have
G,
put
is
it.
it?
No, it's don't just think it like
Okay,
this, right?
What exactly do you mean by that corresponding between the soliton solution on the left hand side and the Fermion on the right hand side?
So what you can see, this is a very interesting feature of this duality. Suppose that this is your fundamental theory, right? So somewhat you are in a situation where this coupling is small, right? And you would like to compute with this theory, and you compute and you learn many things, right? So you would say, and within all your right, that this fermion is a fundamental field, right? It has no structure, whatever you want. So think about it as the electron, right? Good. What this duality shows you is that that thing that you thought was a fundamental field could be thought as a composite of another field, right? And by composite here, let's be a bit loose. In this case, it's a soliton, right? So a classical solution of the equations of motion of this, right? As you can see, it's a nonlinear equation, so people have developed ways to find solutions to that. Okay? This is very cleanly explained in this paper by Mandelstam, by this fact that it's a soliton, and when you see the mapping, you tend to believe. Second example of the duality, I wanted to. So the second example is due to cyber. It's a bit more modern. It's a bit more interesting than that one. But this is a conjecture duality. There is not a proof for the thing that I'm going to say. There are many checks that what I'm going to tell you in the next 3-4 minutes is correct, but there is not a proof as in that case. But it's a very illuminating example. So here it goes. Okay, first consider quantum chromodynamics. That was the theory we are discussing in the very beginning. So quantum chromodynamics has a gauge field typically in the adjoint of some gauge group. Let me not restrict myself to the gauge group SU3. Let me just generalize the gauge groups to SU and C. Right? So this gauge field is in the adjoint of SU and C. Suppose that you have also quarks and anti-quark fields. Let me denote them in this way. Okay, that's QCD. Suppose that you would like to construct a minimally supersymmetric version of QCD. Right? So what people call n equals 1 super QCD. With n equals 1, they mean is the minimal extension you can make. Okay? So if you are familiar at all with supersymmetry, you will know that for every scalar field you have to introduce somewhat. For every field you have to introduce a partner. If the original field is a bosonic field, the partner is a fermionic one. Okay? So if you have a gauge field, okay, there will be a partner that will be a fermion. People call it gauge G. Okay? Never mind. If you have a fermionic field, okay, there will be a partner that will be scaled. Okay? So this is the field content of n equals 1 super quantum chromodynamics. And the Lagrangian, by the way, I don't want to make a big story about this, but the Lagrangian is just as you would imagine, right? So there is, okay, so everything is non-abelian. There is a term like this for this, a term like this for this, a term like this for the fermions and for the others. And for the quarks and anti-quarks, and conversely terms like this so there is nothing really strange about the kinetic terms. All the richness of the system comes in the potential, right? In the interactions via this. And by the way, here also this lambda enters. Okay? So it's here that the n equals 1 is encoded. Right? So again, I don't want to make a big deal about this Lagrangian, but for those of you who are not familiar with supersymmetry, do not fear a supersymmetric theory, right? So it's just the normal theory as you are used to, only that it happens that typically the interactions, they have particular relations that make the theory special somewhat. So let me raise this Lagrangian. It will play no role. Okay, so here we have a field theory with gauge group SU and C. Suppose also that there are NF quarks and NF anti-quarks. So the global symmetries of this field theory are, okay, let me say the symmetries without, let me not say yet the global, are a gauge symmetry, what people in QCD call the chiral symmetry, okay? What people in QCD call the baryonic symmetry. Okay, so in principle you will have UNF cross UNF, right? I don't know, some of you may not be familiar with the following. If you are not, this is just a technical detail. In principle you have UNF cross UNF. That should decompose as SUNF cross SUNF. People call it left and right, people in QCD especially, cross two U1s. One of them is the baryonic U1, the other is an anomalous U1, so people will forget about this. So we'll keep this one. And the fact that you have this extra symmetry called supersymmetry adds for you another U1 that is called R symmetry U1, right? It will play not a very important role in the discussion, the superficial discussion I will make, but plays a very important role in all these supersymmetric dualities. So if anyone wants to know a bit more about this, we can discuss it offline. But okay, these are the symmetries of this particular theory. This one is local, and all of these are global. Okay, so this is one theory. Okay. So Seiberg made a proposal around 1994 that I'm going to describe now. His proposal is that theories of this kind, when becoming strongly coupled, are completely equivalent, exactly in this sense, in the sense that when one becomes strongly coupled, the other, that I'm going to say now, becomes weakly coupled. So, and in this particular example, let me take the following restrictions on. This is just technical matter, but just to say the truth. Okay. So this is just a technical necessity, but in order to say it properly, let me keep these two restrictions. This theory is exactly equivalent in that sense to a field theory like this, that will have a gauge field and a fermion. Notice that this gauge field is not this gauge field. Scalar and a fermion, and another scalar and another fermion. And notice that these fields are not these ones, right? Plus yet another scalar and another fermion, where the gauge group of this field theory is going to be okay, this is the gauge group, this is the local, and the global symmetries are going to be the same. Okay. For let me, what was 2, right? For this duality to be correct, or if you want the proposal, this proposal of Seiberg comes with a. So should I touch again?
Try it. See what happens.
Okay. I just want to draw something here. This proposal should come with the following proviso. These two theories are in principle not exactly the same for all energies, but they are only equivalent when you look at them at very low energies. Let me make a plot that will somewhat. So this is the theory A. This is the theory B. Okay. Both theories might be very different at high energies, right? And if you compute correlation functions of one theory, it will in principle give something completely different from the correlation functions in the other theory. But if you are careful enough and you do this at low energies, and this low is low compared to the confinement scale of this one, then both theories are exactly the same. Notice the following things. And that's why this example, in spite of the technical subtleties that are within it, it illustrates very nicely all the points that I was writing there. The first point that I wrote here was that the degrees of freedom are very different, right? So, see it in this way. Okay, here you have gauge fields and fermions, scalars and fermions, and you may say, look, here I also have gauge fields and fermions, scalars and fermions, but here you have one supersymmetric multiplet or scalar fermion that is not present there. Okay, this one, if this one is not here, all this duality falls immediately. Believe me, I can tell you what are the technicalities there, but you see, in principle, the degrees of freedom are different, even more. notice that these fields are in the adjoint, while these fields are in the fundamental of a different gauge group, right? So one is SUNC, the other is SUNF minus NC. So in principle, the field content is very different, right? So you can have a duality even when the fundamental fields on one side and the fundamental fields on the other are very different. So this is matched nicely. Also is matched nicely, and this is always something that has to happen, that the global symmetries on both sides of the thing, notice these are the global symmetries, are the same. Okay? And it also matches nicely the fact that I'm not illustrating here, but one can compute by looking at how the beta functions of one theory and the other go, is that whenever this field theory goes strongly coupled, so when you go to the infrared, this field theory goes strongly coupled in that way, okay? This one here does exactly the opposite. That this one will be something like this. Right? So if you want this field theory, this theory B, this what people call a magnetic theory, is a theory more like quantum electrodynamics in the sense that it's weakly coupled in the infrared and somewhere will show you a Landau pole, right? And because of that, typically, this theory will need to be defined with an ultraviolet cutoff, etc., etc. So there are many technical subtleties here. This particular technical subtlety happens because I'm restricting to this. But again, lots of technical subtleties, but I hope the idea is more or less clear here. Is it the case? Yes?
Can I ask you a question? The second condition imposed on an F is asymptotic freedom in theory A.
This one, yes.
What's the first one? Can you remind me what's the first one? What does the first
This condition is
No,
as,
the-
this
the other one, can
condition.
you
No,
remind me
okay.
that
What
one,
happened?
where it comes from?
Yeah. So this is a.
No, it's fine. Finish and then you probably go back up.
Sorry, no. It must come from somewhere
Okay.
else. Yes.
Let me save here, Rishi. Let's see. Oh,
Just wait, yes. Go on.
but okay. So this condition. Stop. So you are wondering why?
Yes. I mean, it's very handy, otherwise an F minus NC is negative, which is embarrassing.
Okay. But then you may wonder, and Cyber didn't escape from this problem, what happens when an F is smaller than C, right? So is there something like this? Well, actually, no. But it's very interesting what happens. And probably what I'm going to tell you now should disappoint physicists interested in QCD on the idea of studying this and learning about QCD from supersymmetric QCD. So what happens is the following. When you are in this situation, and you study this minimally supersymmetric QCD theory, you can show, and this can be shown exactly, this is an exact result, that you induce, the quantum mechanics of your theory induces a potential first of all, you can show that you will describe your field theory in terms of a mesonic field. Okay? This mesonic field is going to be basically the thing that you understand by meson, only that here is a superfield, so it has a scalar and a fermionic component. Okay? Good. That the strong dynamics of this theory in this regime will induce for you a potential that in terms of this, the bed, this mesonic field, will look like this. And will never have a minimum. Okay? By the way, this is called Affleck-Dine-Cyber potential or superpotential. Okay? So it's just a way of denoting it. So the argument that people make, or if you want that Cyber made, or Affleck-Dine and Cyber made in that paper, is that this field theory, n equals 1 super QCD, for an F smaller than NC, and in this particular situation in which all the fields are mass less, has not a vacuum. Right? So it's not a well-defined theory. So if you want, in this sense, you are studying the theory from here and up. Right? Just as a technical note, something very peculiar happens for this value and this value. Okay? I can tell you offline what happens. We can talk whenever in these days. And I'll tell you how is the description, how is a strongly coupled description of this example, this case and this case. But from nf equals nc plus 2 and up, in principle, these kind of cyber dualities ideas take place. Okay? There is yet another technical subtlety that when you are in the regime 3/2 NC, 3 NC, something very interesting happens with this duality. Okay? It's what people call the conformal window. In that case, the subtlety is that both these theories, the duality is valid, both those theories are strongly coupled in the infrared. Okay? So I didn't want to go into there just to keep this idea that is going to reappear very soon, just to keep this idea that when one theory is weakly coupled, the other is strongly coupled, because that's typically dominant in duality. Okay?
So this all happens below the conformal window.
What I'm saying, this thing that I'm saying
And
happens
above
from
this
here
NC.
to here. Yeah. Okay. And notice that one of the theories is a QED-like theory. Right? What happens when you enter here, this conformal window, is that both theories are QCD-like theories. They are both strongly coupled in the infrared. There is still a duality between both of them, but it's even more difficult to prove. Right?
So this regime, in this regime, theory A is really a mesonic theory, right? The degrees of freedom are mesons and constant bosons, Goldsteinos, and
Exactly. So in this regime, from NC plus 2 up to 3/2 NC, this theory is a theory of mesons. And if you want, we can discuss tomorrow, but this certainly we'll do it offline, about how supersymmetric theories dislike, not that forbid, of course, dislike chiral symmetry range. But that we will certainly offline. So basically the aim of these examples was just to make 3 points about different dualities. And these 3 points are the degrees of freedom on both sides of these proposed dualities are in principle very different. But the global symmetries are the same. If not, this duality is bound to fail. And that typically when one theory is weakly coupled, the other is strongly coupled. So all the point that I'm going to make now is that ADS-CFT is by the book one of these. Okay? That is, there is nothing in ADS-CFT that should surprise you once one swallows these things. But it's very interesting. So as you wish, we can make a break now, or we can go 15 more minutes and we present this idea, and then we make a break. People decide. So let the power to the people. We all? Yes, 15 more minutes? Okay. Any questions aside from all this? I'm getting out of the part of the lectures that I do not know. So I'm very happy that you are not asking many difficult questions. So let's go for it. As I'm guessing all of you know, was presented by Maldassen in 1997, just as a conjecture, right? But as a conjecture has not any less degree of validity as these ones that are conjectures. Right? This one I was telling you is proven, but you can find other dualities in 2 dimensions that are not proven, or other dualities in other dimensions that are not proven. So this one, it falls within that equivalence class. The only difference is that it's much more interesting from what you will see. You will see it's much more interesting. So the duality is between two very different systems. One is a quantum field theory in 4 dimensions, in flat space, if you want. And the other side of this duality is string theory, a particular string theory. If you want, let me say it, a theory of gravity. And let me say it in this way. A theory of quantum gravity in a particular space. Or if you want, formulated in a particular space. That as you are familiar with the string theory, wants to be formulated at least in 10 dimensions. Right? Okay. So this is the bottom line of the duality. So you see, as I'm going to say it now in more detail, it's a bit more striking, certainly a bit more striking, that this duality between a real scalar and a Dirac fermion in 2 dimensions, or these gauge theories, 2 gauge theories, all of them in the same 4 dimensions. So this is a bit more striking, at least in that sense, right? It's a quantum field theory and a quantum theory of gravity, a theory of strings, in different space dimensions, right? So this has all the ingredients to be wrong, and it does not, right? So it does not fail. So it's really a very good insight from many perspectives. Good, details about this. The quantum field theory, as I'm guessing many of you know or read, is n equals 4 super Young Mills. I'm going to give some details about this. So remember when I was telling you n equals 1 super QCD, and I was saying, well, if you have a gauge field, you will have a fermion. Okay, that's with n equals 1. But when you increase the number of supersymmetries, I'm saying this for those of you who are not familiar with supersymmetry, the moment you increase the number of supersymmetries, not only you will have to increase the number of these fermions, but also you will have to add some scalars. Okay? So it happens in this particular example that you will have to have 4 of these fermions and 6 of these scalars. By the way, this index A, all this is with gauge group SU and C. Right? They can see the number you want in principle. So this A will go from 1 to NC squared minus 1. So some characteristics about this field theory are the following. The first interesting characteristic is that, of course, the field theory is formulated in 4 dimensions, so it will naturally, unless you touch it and it will lose its virtues, it will have Lorentz invariance. Right? It happens, and this is due. Anyway, this is due to the high amount of symmetry that actually is not SO13, but it's actually the conformal group what really appears. Right? So this, by the way, is the conformal group in 4 dimensions. This is just a side remark, right? Before, when I was saying, look, we will really not care about the precise Lagrangian of these theories. In this case, we will really not care, at least in these lectures, about the precise Lagrangian of this theory, but it goes as you can imagine. Right? So you will have non-abelian gauge field, dynamics for the scalar, and dynamics for the fermions. Right? And here there are the 6 of them, and sorry, the 4 of them, and here the 6 of them. And then again, as it happened in the n=1 example, all the richness of the system is in the potential that makes them interact. Okay? So it's due to this potential, and you touch it a bit, and all these properties I'm going to say do not occur. So this one does occur, but this one does not. Right? It is due to that potential that the field theory has what are called 16 supersymmetries. This is a technical point, plus 16 superconformal symmetries. I can clarify this point a bit more if needed. But this is what people in string theory call this a maximally supersymmetric field theory. Right? It cannot have more than that number of supersymmetries in 4 dimensions. A field theory in 4 dimensions. So the point I would like to emphasize about this side of this description, let me erase this Lagrangian. The point I would like to emphasize about this side of this description is that this is a conformal theory. So unlike QCD, unlike these examples of super QCD, this or those, or unlike quantum electrodynamics, this field theory has a gauge coupling that does not change with energy. Okay? So you measure it at any energy, and this gauge coupling, and actually, let me take this combination that people call the Toft coupling, is the gauge coupling times the number of colors. That's actually the relevant expansion parameter. For any energy is the same. So it could happen that is small, or that is larger than 1. You decide. It's something that you tune, okay? But it's a constant. Right? You decide to tune. Right? That is not dynamically determined. But once you tune it, you have either a perturbative theory or a non-perturbative theory. So that's about this particular side of the duality. On this side of the duality, and again I think I'm going to say things that many of you know very well. The idea is that this particular string theory in a particular spacetime are now being more concrete. Are the type 2B string theory on a spacetime of the form anti-de Sitter space of 5 dimensions and a phi sphere. I'm going to write this spacetime in a second. So, but for you to have a picture of the thing, what's going on here is that we will have 4 dimensions. 4 dimensions. A radial direction I'm going to call U, and a phi sphere with 5 angles, right? Parameterized by phi angles. So this space-time, the metric of this space-time that I'm about to write, will contain a 4-dimensional part, a radial direction external to this 4-dimensional part, and a phi sphere with 5 angles. So let me write this metric in detail. So if you are not familiar with the metric of a phi sphere, never mind at this point. Just if you know the 2 sphere, you know actually the phi sphere. I can tell you how to generalize later. This bit of the space called anti-de Sitter phi. Well, this bit, as you can imagine, is the phi sphere. So when we resume in 10 minutes or so, I'll try to make the point for how all these things, right, are present in this structure. Okay? And I'll try to discuss some other things about this duality. Okay? So let's make 10 minutes is good.
Yeah.
Okay? So it's enough for those who want to leave and leave me alone. And all right, the 10 minutes. Let's meet in 10.